You are sitting in a room you trust. The floor beneath you feels solid. The air around you behaves as expected. Objects stay where you leave them. Causes produce effects. Nothing about this moment seems remarkable. Reality appears stable, predictable, and mostly indifferent to your presence. You have been taught to believe that beneath this familiarity lies randomness, that the universe, at its deepest level, is governed by chance, that events unfold statistically, not intentionally. That order is something humans project onto chaos, not something built into reality itself. This belief is comforting. Randomness suggests neutrality. It implies that nothing is watching, nothing is guiding outcomes, and nothing is quietly arranging events behind the scenes. If the universe is random, then it cannot prefer one outcome over another. It cannot lean. It cannot aim. But this sense of safety begins to erode when you look closely at how reality actually behaves. At the smallest scales ever measured, outcomes are not merely uncertain. They are constrained in ways that resemble preference. Physical systems explore all possibilities, yet consistently settle into patterns that maximize stability, efficiency, or symmetry. Structures emerge not by accident, but by necessity. Laws do not merely allow order, they enforce it. Even more unsettling, many of these patterns appear before anything can interact with them, before particles collide, before observers measure, before time, as you experience it, has a chance to unfold. The question is no longer whether randomness exists. The question is whether randomness is fundamental at all. And if the universe is not random, then what exactly is it doing instead? One, the comfort of chance. You grow up assuming that chance is the final explanation. Coins land heads or tails. Mutations occur randomly. The universe expands without intention. Randomness becomes the intellectual buffer between cause and meaning. It tells you that events happen, but not for reasons that matter. This assumption feels scientific. It feels modern. Yet it quietly functions as a belief system, one that shields you from asking why certain outcomes appear far more often than others. From an early age, you are taught to treat randomness as a stopping point. When a result surprises you, chance explains it. When patterns break, chance absorbs the shock. It is a concept that requires no further inquiry. There is no deeper mechanism to uncover, no structure to confront. Randomness ends the conversation. This is why it feels safe. If outcomes are random, then the universe is neutral. It does not aim. It does not prefer. It does not lean toward one future over another. You are free to interpret meaning locally while accepting that, at the deepest level, nothing is organized around you. Randomness becomes a guarantee of indifference. But this comfort depends on a subtle assumption that randomness is fundamental, that beneath all structure, beneath all law, there is no hidden bias, no direction, no constraint beyond probability itself. When you begin to examine how chance actually functions in physical theories, that assumption starts to weaken. In everyday language, random means unpredictable. But in science, randomness is rarely unstructured. A coin does not land heads or tails arbitrarily. Its outcomes depend on initial conditions, forces, and constraints you cannot measure precisely. What feels random is often the result of complexity, not absence of cause. You accept randomness because it aligns with your limited perspective. The same pattern appears at larger scales. Genetic mutations are described as random, yet the space of viable mutations is severely restricted. Most changes destroy function. a narrow subset persists. Evolution does not wander freely. It moves within boundaries defined by chemistry, physics, and survival itself. Chance operates, but only where law permits it. This distinction matters because it reframes what randomness actually does. It does not create all possibilities. It selects among those already allowed. The universe does not roll dice across an infinite table. It rolls them inside a small, rigid box. When you apply this lens to cosmology, the comfort of chance becomes harder to maintain. You are told the universe began by accident, that its structure emerged from fluctuations. That order is an afterthought layered onto chaos. Yet the earliest conditions appear finely constrained. The laws that govern expansion, particle behavior, and energy distribution were present from the beginning. Without them, chance would have produced something else entirely, or nothing at all. Randomness did not write the rules. It operates inside them. This raises a disturbing question. If chance requires structure to function, then randomness cannot be the deepest explanation. It depends on something more basic, something that defines what outcomes are even possible, and that something is not random. You may resist this conclusion by pointing to probability distributions, uncertainty principles, and statistical behavior, but these do not eliminate structure. They formalize it. They specify with mathematical precision how uncertainty is allowed to behave. They draw boundaries around chance and call it fundamental, even as those boundaries remain fixed. The comfort of chance begins to look less like a discovery and more like a preference. It allows you to believe that meaning is optional, that patterns are coincidental, that no outcome carries more weight than another. Yet the universe repeatedly contradicts this belief. It forms stars instead of chaos, atoms instead of noise, laws instead of arbitrariness. You are not disturbed by randomness itself. You are disturbed by what its absence might imply. Because if chance is not the final explanation, then outcomes are not merely happening, they are being shaped. Not by intention, not by consciousness, but by constraints so deep they feel invisible. The universe may not care about you, but it does care about consistency, about stability, about rules that do not bend. Randomness was never your shield from meaning. It was your shield from structure. And once that shield weakens, you are left facing a universe that does not simply allow events to occur, but quietly insists on how they unfold. 2. Patterns that refuse to disappear. You expect randomness to produce noise. Instead, you find structure everywhere. Galaxies form along filaments. Chemical reactions settle into stable configurations. Biological systems converge on similar solutions across vast distances. These are not isolated coincidences. They are recurring outcomes that emerge regardless of initial conditions. Randomness alone does not easily explain convergence. At first, you are taught to treat these patterns as accidents that survived. Given enough time and enough trials, order eventually appears. This explanation sounds reasonable until you notice how often the same forms repeat. Spiral galaxies dominate the cosmos. Crystals arrange themselves into precise lattices. Fluids form vortices. Life independently discovers eyes, limbs, and neural structures. Different starting points lead to the same destinations. If chance were truly in control, outcomes would scatter. Variations would multiply without preference. Yet reality behaves differently. It funnels complexity into narrow channels. Possibilities collapse into a small set of stable arrangements, while countless alternatives never appear at all. This is not a poetic observation. It is measurable. In physics, systems naturally move toward attractor states. These are configurations that resist disturbance. Once reached, they persist. A pendulum settles at rest. A chemical reaction reaches equilibrium. A planet clears its orbit. These outcomes are not chosen consciously, but they are favored mathematically. The equations governing motion, energy, and interaction make some states overwhelmingly more likely than others. Randomness operates during the journey, but not at the destination. You see this most clearly when systems are pushed far from equilibrium. Chaos emerges briefly. Motion becomes unpredictable. Yet even then, the chaos is temporary. Given time, order returns. Not necessarily the same order as before, but a recognizable one. Structure reasserts itself. This persistence raises an uncomfortable question. Why should the universe prefer stability? No physical law requires complexity to resolve into neat forms. Noise could dominate indefinitely, yet it does not. Instead, patterns self-organize. Local order arises spontaneously, even as overall entropy increases. This coexistence of disorder and structure is not an exception. It is the rule. You may try to dismiss this by invoking statistics. With enough trials, rare outcomes occur. But convergence is not rarity. It is repetition. It is the same solutions appearing again and again under different circumstances. That is not what blind chance predicts. In chemistry, molecules assemble into predictable shapes because of energy minimization. In biology, organisms converge on similar traits because certain designs solve universal problems. In cosmology, matter traces filaments because gravity amplifies small differences into large-scale structure. Each explanation is valid, yet all of them share a deeper feature. They rely on constraint. The universe does not explore all possibilities equally. It filters them. It suppresses most options and amplifies a few. The result is not randomness decorated with order, but order emerging because randomness is limited. This limitation is easy to overlook because it is invisible. You do not see the outcomes that never occur. You only see what survives. But absence is informative. When the same patterns dominate across scales, it suggests that reality is not free to behave arbitrarily. Even chaos theory supports this conclusion. Chaotic systems are sensitive to initial conditions, but they are not unbounded. They trace strange attractors. Their motion appears random, yet it remains confined to specific regions of state space. Disorder dances inside a cage. The more deeply you examine these systems, the clearer it becomes that randomness is not erasing structure. It is revealing it. Variation exposes which configurations endure and which collapse. Chance becomes a probe, not a cause. This reframes how you understand the universe. Patterns are not accidents that happen to persist. They are the only outcomes that could persist. Everything else dissolves too quickly to matter. The discomfort comes from what this implies. If structure is inevitable, then the universe is not improvising. It is unfolding, not according to a script you can read, but according to constraints that quietly eliminate alternatives long before you notice them. Patterns refuse to disappear because they were never optional. They are the shapes reality settles into when it has no other choice. 3. Laws that precede events. You assume laws describe what happens after the universe exists, but physics increasingly suggests the opposite. The mathematical structure comes first. The equations do not emerge from reality. Reality conforms to them. This reverses the intuitive order. Events no longer generate rules. Rules generate events. You are used to thinking of laws as summaries. Gravity explains falling objects because objects already fall. Thermodynamics explains heat because heat already flows. In this view, laws are human inventions, compressed descriptions of behavior observed after the fact. The universe acts first. Mathematics arrives later to organize the evidence. But this intuition quietly breaks down the deeper you look. In modern physics, equations do not merely describe patterns, they constrain what can exist at all. Certain particles appear not because they were observed, but because mathematical consistency demands them. Entire classes of phenomena are ruled out before any experiment is performed, not by observation, but by structure. You encounter this most clearly when predictions precede discovery. Equations imply entities that have never been seen. Years later, experiments confirm them. The mathematics was not inferred from reality. Reality complied with mathematics. This inversion is unsettling because it removes events from the foundation. What happens is no longer primary. What is allowed becomes decisive. In quantum field theory, particles are excitations of underlying fields defined mathematically. The field exists in the equations before any particle appears. An event is not a basic unit of reality. It is a manifestation of a deeper formal structure temporarily expressing itself. This means that before anything happens, the space of possible happenings is already fixed. You may try to resist this by arguing that mathematics is just a language, a convenient way to encode relationships. But this defense weakens when you realize that different mathematical structures imply different universes. Alter the equations slightly, and reality collapses. Atoms cannot form. Time behaves differently. Space loses coherence. The universe you inhabit is not just one that follows laws, it is one that survives them. This suggests that laws are not passive descriptions layered onto chaos. They are active constraints that sculpt chaos into something stable enough to exist. Without them, events would not merely behave differently. They would fail to occur in any meaningful sense. Even more troubling, these laws appear timeless. They do not evolve as the universe unfolds. The equations governing particle interactions today are the same ones that governed them billions of years ago. The universe changes, the rules do not. This temporal asymmetry matters. If laws were emergent, you would expect them to crystallize gradually. Early reality would be lawless, refining itself over time. But evidence points in the opposite direction. The earliest moments were governed by the same mathematical consistency as the present, even if expressed at extreme energies. Order did not slowly arise. It was present from the start. This forces you to reconsider what an event actually is. An event feels like something that happens independently, something that adds novelty to the world. But if events are generated by rules that pre-exist them, then novelty is constrained. What appears new is simply a rearrangement within a fixed framework. The universe is not improvising, it is executing. This does not mean the future is fully predictable. Complexity, sensitivity, and uncertainty still dominate experience. But unpredictability is not the same as absence of structure. A chess game is unpredictable, yet every move is governed by rules that existed before the first piece was placed. In this analogy, you are not watching laws respond to events. You are watching events explore the limited space those laws permit. The discomfort comes from recognizing that the deepest layer of reality may not be physical at all. It may be abstract, mathematical, logical, something that does not occur in time, but gives time its structure. If that is true, then the universe is not built from events. It is built from constraints. And what you experience as reality is what happens when those constraints are allowed to express themselves moment by moment without ever being questioned. 4. Probability. with boundaries. Quantum mechanics is often described as probabilistic, yet those probabilities are sharply constrained. Outcomes are random only within strict limits. Certain results are forbidden entirely. Others dominate. This is not chaos. It is randomness guided by invisible fences, shaping what can and cannot occur. You are taught that at the quantum level, reality becomes unpredictable. Particles appear to exist in multiple states at once. Measurements yield different results each time. Probability replaces certainty. This framing suggests a fundamental looseness beneath the surface of the world, as if nature finally lets go of structure when you look closely enough. But when you examine how quantum probability actually behaves, the looseness vanishes. Quantum outcomes are not drawn from an open field of possibilities. They are sampled from a precisely defined distribution. The probabilities are calculated exactly. They obey equations with no tolerance for deviation. You never observe a particle with impossible energy. You never measure a forbidden spin. Some outcomes simply do not occur, no matter how long you wait. Chance operates, but only where law allows it. This distinction becomes clearer when you consider the wave function. It encodes every possible outcome a system can produce, but it also encodes which outcomes are excluded. The mathematics does not hesitate. It assigns zero probability to certain states. These states are not rare. They are impossible. This means uncertainty does not imply freedom. It implies constraint without predictability. You experience this every time a measurement is repeated. Individual outcomes vary, but the statistical pattern remains fixed. After many trials, the distribution converges with remarkable precision. The randomness averages out, revealing an underlying order that was always there. If probability were fundamental chaos, these patterns would drift. They would fluctuate, but they do not. They lock in. This stability is unsettling because it suggests that randomness is not erasing structure. It is expressing it. You can think of quantum probability not as a lack of rule, but as a rule that governs how unpredictability is allowed to appear. It specifies the shape of uncertainty. It tells reality how to be uncertain without becoming incoherent. This is why quantum mechanics remains one of the most precise theories ever constructed. Its predictions are confirmed to extraordinary accuracy. If probability were truly free, such precision would be impossible. The invisible fences become even more apparent when you examine quantum interference. Probabilities do not simply add. They combine in ways that depend on phase, symmetry, and coherence. Paths cancel each other out. Some outcomes vanish entirely due to destructive interference. Others amplify. This is not what randomness looks like in ordinary experience. It is closer to a filtering process, where chance explores options that have already been carefully arranged. The universe does not ask what might happen. It asks which allowed outcome will manifest this time. This framing also reshapes how you understand measurement. When you observe a quantum system, you are not creating possibilities. You are selecting among predefined ones. The system collapses into a state it was already permitted to occupy. Nothing genuinely new enters existence. The unsettling implication is that uncertainty exists without openness. The future is not a blank canvas. It is a constrained landscape where motion is permitted, but boundaries are fixed. You may object that hidden variables could restore determinism, or that interpretations differ. But regardless of interpretation, the structure remains. All viable models preserve the same constraints. No interpretation allows forbidden outcomes. Probability, then, is not the opposite of law. It is law operating under conditions of incomplete information. What you call randomness is what remains when rules are too deep to track directly. This realization strips chance of its mystery. It is no longer a fundamental ingredient of reality. It is a surface effect, arising when fixed constraints interact with limited access. The universe is not undecided. It is undecipherable. And that difference matters because it means that even at its most uncertain, reality is still following rules you did not choose and cannot escape. 5. The illusion of equal possibility. When you hear the word random, you imagine all outcomes treated equally, but nature does not behave this way. Some configurations are overwhelmingly favored. Energy flows downhill. Entropy increases. Systems relax into states that minimize tension. The universe repeatedly chooses the same destinations. This intuition of equal possibility is deeply ingrained. Randomness, as you imagine it, is fair. Every outcome has the same right to occur. Nothing is biased. Nothing is preferred. This idea feels clean, democratic, and consistent with a universe that does not care what happens inside it. But the moment you examine physical processes, this symmetry collapses. In thermodynamics, systems do not wander aimlessly through all available states. They move toward equilibrium. Heat spreads, pressure equalizes, concentrations diffuse. These processes are described statistically, yet the direction is unmistakable. The system overwhelmingly favors states that maximize entropy, not because they are chosen, but because they dominate the space of possibilities. This dominance is not subtle. High entropy states outnumber low entropy ones by astronomical margins. When a system evolves, it is not selecting randomly from equal options. It is falling into the largest basin available. The outcome feels inevitable because mathematically it nearly is. You see the same asymmetry in energy landscapes. Atoms settle into lowest energy configurations. Molecules fold into stable shapes. Chemical reactions proceed toward products that release energy. These are not preferences layered on top of randomness. They are consequences of constraint. Certain arrangements are simply more accessible than others. Random motion does not erase this imbalance. It accelerates it. Even when fluctuations push a system briefly uphill, it returns downhill almost immediately. Equal possibility exists only in abstraction. Reality weights its options heavily. This weighting extends beyond thermodynamics. In classical mechanics, stable orbits dominate over unstable ones. In quantum systems, ground states dominate over excited states. In cosmology, matter clumps rather than disperses uniformly once gravity takes hold. Across domains, the universe exhibits a consistent bias toward certain configurations. You might try to explain this away by saying that favored outcomes are merely more probable, not guaranteed. That chance still operates. This is true, but incomplete. The issue is not that some outcomes happen more often. It is that most outcomes effectively never happen at all. The space of allowed states is not evenly populated. It is sharply skewed. When you say the universe could have evolved differently, you are technically correct. But the overwhelming majority of alternatives are so unstable, so short-lived, or so inaccessible that they might as well be forbidden. Equal possibility exists only on paper. This becomes especially unsettling when applied to initial conditions. You are told that the early universe could have started in countless ways, yet only an extraordinarily narrow range leads to the universe you observe. The rest collapse too quickly, expand too fast, or fail to form structure entirely. The universe did not sample these options fairly. It settled into one of the few states that persist. This realization changes how you understand chance. Randomness does not explore all futures. It explores the steepest paths through a landscape already shaped by law. The dice are loaded not by intention, but by geometry, by the shape of possibility space itself. The illusion of equal possibility survives only because you do not see the paths that vanish instantly. You experience only what remains. Stability masquerades as neutrality, but neutrality is absent. The universe repeatedly chooses the same destinations because those destinations are where motion naturally ends, not because they are selected, but because everything else dissolves too quickly to matter. Randomness is not a flat field. It is a slope, and once you recognize that slope, the idea of a universe that treats all outcomes equally becomes impossible to maintain. 6. Order from nothing. Early cosmology suggests the universe began in an extremely low entropy state. This is not what randomness predicts. If everything were equally likely, disorder should have dominated from the beginning. Instead, the universe started improbably ordered, then unfolded predictably from that point forward. You are told that the universe began hot, dense, and chaotic. A violent beginning, a turbulent origin. But when physicists examine the conditions required for the universe to evolve the way it did, a contradiction appears. Beneath the heat and density, the initial state was astonishingly simple. Smooth, uniform, highly ordered. This simplicity is not intuitive. In most systems, order is rare. If you randomly shuffle particles, you almost never get structure. Disorder dominates by sheer volume. There are vastly more ways for things to be messy than neat. This is the statistical foundation of entropy. And yet, the early universe was neat. Matter was distributed with extraordinary uniformity. Deviations were tiny, precise, and balanced just enough to allow galaxies to form billions of years later. Too smooth, and nothing would clump. Too rough, and everything would collapse too quickly. The universe began on a knife edge. This is not what chance alone predicts. If the universe were randomly initialized, high entropy should have been the default. Structure should have been absent from the start, not emerging gradually. Time's arrow should have been meaningless. There would be no clear direction from past to future. But the arrow exists because the beginning was special. Low entropy is not a generic starting point. It is an exception that demands explanation. Yet physics offers no mechanism that naturally produces such a beginning from randomness alone. The equations describe how entropy increases, not why it started low. This gap is quietly unsettling. You may try to explain it away by saying that entropy is relative or that gravity complicates the picture. Gravity does matter. It allows local order to increase even as global entropy rises. But gravity does not explain why the universe began in a state where this process could unfold so elegantly. It explains growth, not origin. The deeper problem is that entropy defines time itself. The flow you experience as past to future is a consequence of entropy increasing. Without a low entropy beginning, time would not have a direction. Cause and effect would blur. Memory would fail to accumulate. Experience would collapse into noise. Your existence depends on that initial order. This dependency raises a disturbing implication. The universe did not merely allow order to emerge. It required it from the start. The initial conditions were not neutral. They were precise. Not precise in the sense of intention, but precise in the sense of constraint. The universe began in one of the rare states that make history possible. Everything you observe, from stars to thoughts, traces back to that improbable simplicity. Randomness alone does not privilege such states. It avoids them. You may be tempted to invoke inflation, multiverses, or selection effects. These ideas attempt to dilute the improbability by expanding the sample size. If enough universes exist, one might start ordered. But this does not remove the problem. It relocates it. The larger framework must still permit low entropy beginnings. The rules that generate universes must themselves be structured. Order does not disappear. It moves up a level. The discomfort comes from realizing that the universe did not begin in chaos and stumble into order. It began ordered and then relaxed. The unfolding you call history is not creation. It is degradation, a slow drift away from an initial clarity you never witnessed. Randomness enters later as entropy grows. Uncertainty increases over time, not the other way around. The universe starts legible and becomes noisy. This inversion matters. It suggests that order is not something the universe fights to achieve. It is something it slowly loses. And that loss follows predictable rules laid down from the beginning. Order did not come from nothing. It came first, and everything else followed. 7. Fine-tuning without adjustment. The constants of physics appear precisely set to allow structure, chemistry, and complexity. Slight deviations would erase stars, atoms, or time itself. This fine-tuning does not prove intention, but it does challenge the idea that outcomes are indifferent. The universe operates on a narrow ridge of possibility. You are often told that these constants simply are what they are. Numbers, measured, recorded, and accepted. The strength of gravity, the charge of the electron, the ratio of forces that determine whether matter clumps or disperses. Treated individually, they feel arbitrary. Taken together, they form a delicate system that barely holds. What makes this unsettling is not that the values are precise, but that they are mutually dependent. Change one slightly, and the others lose meaning. Increase gravity just a little, and stars burn too fast to support chemistry. Decrease it, and matter never collapses into stars at all. Adjust the electromagnetic force, and atoms cannot remain stable. Alter the cosmological constant, and space either collapses immediately or expands so rapidly that structure never forms. These are not exaggerated sensitivities. They are mathematical consequences. You may try to reassure yourself by saying that these constants are simply measured facts, not mysteries. Physics does not ask why they have these values. It only describes what follows from them. But this avoidance is itself revealing. The question persists because the margin is so thin. The universe is not robust to variation. It is fragile. This fragility undermines the idea that outcomes are treated equally. If all configurations were equally acceptable, complexity would be common. But it is not. The vast majority of possible universes are sterile. They contain no atoms, no chemistry, no timescales that allow persistence. Only a narrow band of conditions permits anything interesting to happen. Randomness does not favor narrow bands. You might be tempted to frame this as selection bias. Of course, you observe a universe that supports observers. If it did not, you would not be here to notice. This reasoning is logically correct, but incomplete. It explains why you observe such a universe, not why such universes are even possible. The deeper issue is that the space of possibilities itself is uneven. Life-permitting conditions are not scattered generously. They are confined to tight corridors. The rules that define these corridors are mathematical, not biological. They exist before life, before stars, before matter organizes at all. This shifts the discomfort away from intention and toward constraint. The universe does not need to be designed to be constrained. A lock does not require a hand to limit which keys fit. Its shape alone enforces restriction. In the same way, the equations governing reality appear to carve out only a few viable configurations. The fine-tuning problem is unsettling, not because it implies purpose, but because it implies non-neutrality. The universe does not behave as if all outcomes are equally welcome. It behaves as if only a few outcomes are allowed to persist. You see this even when you strip the problem of life entirely. Long before biology, the constants determined whether time had a direction, whether particles could interact meaningfully, whether energy could settle into stable forms. Complexity was not added later, it was enabled at the foundation. This suggests that fine-tuning is not an adjustment applied after the fact. It is a precondition. The universe is not correcting itself as it goes. It is operating within limits that were fixed from the start. You may argue that future theories will explain these constants as necessary rather than contingent, that deeper laws will force them to take the values they do. But this does not remove the unease, it intensifies it. Because necessity is stronger than chance. If the constants could not have been otherwise, then the narrow ridge of possibility was not chosen. It was unavoidable. Reality had no freedom to be different. Fine-tuning without adjustment is not evidence of care. It is evidence of confinement, and a universe confined to such a narrow path is not indifferent. It is constrained so tightly that even existence itself appears to depend on precise conditions that were never negotiable. 8. Symmetry as a guiding principle. Physical laws are built around symmetries. These are not aesthetic preferences. They are mathematical constraints that dictate conservation, stability, and interaction. Symmetry is not imposed by observers. It is woven into the behavior of reality at every scale. You are used to thinking of symmetry as visual balance, a mirror image, a pleasing alignment. But in physics, symmetry is far more severe. It is not about appearance. It is about invariance. If you perform an action and nothing changes, a symmetry exists. And where symmetry exists, laws follow. This connection is not philosophical. It is formal. When a system remains unchanged under certain transformations, specific quantities must be conserved. Energy, momentum, charge. These are not assumptions. They are consequences. Conservation laws do not exist independently. They are enforced by symmetry itself. This means that some of the most fundamental features of reality are not chosen. They are required. You do not conserve energy because energy is important. Energy is conserved because the laws of physics do not change over time. You do not conserve momentum because objects like to keep moving. Momentum is conserved because space behaves the same everywhere. The universe does not privilege one location or moment over another. Symmetry is the reason. This realization shifts how you understand causality. Conservation laws are not responses to events. They are restrictions on what events are even possible. You cannot violate them not because you lack power, but because reality does not permit such outcomes to exist. Even when symmetry breaks, it does so according to strict rules. Early in the universe, symmetries shattered as conditions changed. Forces separated. Particles acquired mass. Structure emerged. But these breakings were not random. They followed precise mathematical pathways. New asymmetries appeared, but always within a framework that preserved deeper invariances. This is not creative freedom. It is controlled transformation. You see symmetry guiding behavior even in quantum mechanics, where outcomes feel uncertain. Wave functions respect rotational symmetry. Particle interactions obey gauge symmetries. Probabilities depend on conserved quantities. Even randomness conforms to invariant structure. Nothing escapes. What makes this unsettling is that symmetry operates silently. You do not experience it directly. You experience consequences. The fact that objects persist, that time flows consistently, that interactions repeat reliably. All of this depends on symmetries you never perceive. If these symmetries were slightly altered, the universe would not become different in interesting ways. It would become incoherent, conservation would fail, stability would vanish, events would not accumulate meaningfully. Symmetry is not decoration, it is scaffolding. You may try to argue that symmetries are discovered, not imposed, that they are simply properties of our mathematical descriptions. But this distinction fades when experiments confirm predictions derived purely from symmetry arguments. Particles appear because symmetry requires them. Interactions behave because invariance demands it. The universe respects symmetry even when no observer enforces it. This respect has consequences. It narrows the space of possibilities. Out of countless conceivable laws, only those consistent with symmetry can operate without collapsing. The universe selects these not by choice, but by necessity. Symmetry also explains why the universe feels reliable, why yesterday's experiments work today, why distant galaxies obey the same rules as your surroundings. Uniformity is not coincidence. It is a requirement imposed by invariance. This consistency can feel comforting. It allows science to function, but it also implies that the universe is deeply constrained. It cannot surprise you arbitrarily. It can only surprise you within the boundaries symmetry allows. Randomness may appear at the surface, novelty may emerge locally, but underneath, symmetry ensures that the same principles always apply. The unsettling conclusion is not that the universe is symmetrical. It is that symmetry decides what can exist before anything exists at all, and once those decisions are made, everything that follows is forced to obey. 9. The arrow that only points one-way time moves forward, never backward. This asymmetry defines your experience of existence, yet the fundamental laws do not require it. The arrow of time emerges from statistical behavior, but once established, it dominates everything. Randomness does not explain its persistence. You experience time as irreversible. Memories form in one direction. Causes precede effects. You grow older, never younger. Broken objects do not reassemble. Heat does not spontaneously flow from cold to hot. This directionality feels so obvious that it seems built into reality itself. But when you examine the equations governing fundamental physics, that certainty dissolves. At the deepest level, the laws that describe particles, forces, and interactions are largely time-symmetric. If you reverse the direction of time in these equations, they still work. The mathematics does not care which way time flows. Nothing in the fundamental rules demands a preferred direction. This creates a profound contradiction. Your entire experience depends on an arrow of time that the laws themselves do not enforce. The usual explanation points to entropy. Systems evolve from low entropy to high entropy because high entropy states are overwhelmingly more numerous. Given enough particles and interactions, disorder becomes statistically inevitable. Time's arrow in this view is not fundamental, it is emergent. This explanation is accurate, but incomplete. Entropy explains why time has a direction once a low entropy state exists. It does not explain why that direction never reverses. It does not explain why the arrow is so stable, so universal, and so deeply embedded in every process you observe. Statistical behavior alone predicts fluctuations. Given enough time, entropy should occasionally decrease. Order should briefly reappear. In small systems, this happens. In principle, nothing forbids a glass of water spontaneously freezing in a warm room or shattered fragments reassembling. Yet, in practice, you never see it. The arrow of time is not merely a tendency. It is enforced with near absolute reliability. Across cosmic scales, from the evolution of stars to the decay of particles, processes align with the same temporal direction. The universe does not hesitate. This consistency is unsettling because it suggests that the arrow of time is not just a statistical accident. It behaves more like a constraint. Once time begins flowing in one direction, it never relaxes its grip. You may argue that the universe is simply too large for meaningful reversals, that fluctuations are drowned out by scale. But scale alone does not create prohibition. It only makes reversals unlikely, not impossible. Yet impossibility is what you observe. More troubling still, time asymmetry infects processes that are not obviously statistical. Quantum measurements produce irreversible records. Information spreads, but does not reconverge. Causes imprint themselves on the future in ways that cannot be erased. The arrow reaches into everything. This suggests that once the arrow of time emerges, it becomes self-reinforcing. Each irreversible process creates conditions that enforce further irreversibility. Memory, structure, causality, and identity all depend on this reinforcement. Without it, experience would fragment. You do not simply move through time. Time structures what you are allowed to experience. This raises a deeper question. If the laws do not require time to flow forward, why does it never fail to do so? Why is the arrow universal rather than local? Why does the universe not contain regions where time runs differently? No experiment has ever detected such regions. The arrow of time behaves as if it were imposed globally, even though no law explicitly commands it. Once established, it dominates reality with a rigidity that randomness cannot explain. The unsettling implication is that time's direction may be more fundamental than the laws that allow it, that the universe may be built to forget, not remember, to lose information in one direction only. Randomness introduces uncertainty, but the arrow of time introduces commitment. Once an event occurs, it cannot be undone. Once a choice is made, alternatives vanish permanently. Time does not explore possibilities, it erases them. And whatever set that direction in place did not ask for permission from the laws that followed. 10. Causality under pressure. At quantum scales, cause and effect blur. Some experiments suggest outcomes can influence earlier states, not metaphorically, but mathematically. If true, randomness becomes difficult to define. Events may not simply happen. They may be constrained by conditions that exist outside linear time. You are taught that causality is sacred. A cause precedes an effect. The past generates the present, and the present generates the future. This ordering feels inseparable from logic itself. Without it, prediction collapses, responsibility dissolves, meaning loses sequence. But when you examine the structure of quantum theory, this clarity begins to fracture. In certain experiments, the outcome of a measurement appears to determine which past description of a system is valid. The mathematics does not assign a single, fixed history until the final result is known. Multiple possible pasts coexist, and only later does one become consistent with the observed outcome. This is not interpretation layered onto data. It is how the equations behave. You may try to reframe this as a limitation of knowledge. Perhaps the past was always fixed, and you simply did not know it. But quantum theory resists this escape. Attempts to preserve classical causality require introducing hidden structures that themselves create contradictions elsewhere. Bell-type experiments close many of these loopholes. The universe does not behave as if all properties were determined in advance. What you are left with is a form of causality that does not flow cleanly forward. In delayed choice experiments, decisions made in the present appear to affect how a particle behaved in the past, not by changing the past, but by determining which past was ever allowed to be meaningful. Until the outcome is fixed, the system's history remains undefined. This undermines a core assumption you rarely question, that events have a single, objective sequence independent of observation. If the past is not fully settled until the future arrives, then cause and effect are not arranged along a simple line. They are linked by consistency constraints that span time rather than follow it. This is where randomness begins to lose its footing. Randomness assumes a sequence. First, possibilities exist. Then, one is selected. But if the selection reaches backward to constrain what possibilities ever existed, then chance is no longer local in time. It becomes global. Outcomes are not chosen moment by moment. They are selected in a way that preserves coherence across the entire process. You can think of it as a puzzle that must fit together all at once. The beginning, middle, and end must agree. Not because the future reaches back with intention, but because inconsistent histories are mathematically excluded. Causality, in this view, is not broken. It is reorganized. Instead of causes pushing effects forward, the universe enforces self-consistency across time. Events occur only if they can coexist with outcomes that come later. Possibilities that would lead to contradiction are silently removed. This mechanism feels foreign because it does not resemble experience. You feel as though you act first and consequences follow. But at the quantum level, the structure may be reversed. Consequences constrain what actions were ever possible. This does not allow paradoxes. You cannot send information to your past self. The constraints are subtle. They preserve causality at the level of observable events while abandoning it at the level of underlying description. The result is unsettling. Time remains ordered in experience, but not in explanation. If events are constrained by conditions outside linear time, then randomness is not simply ignorance of causes. It is ignorance of global consistency. What appears as chance may be the residue left after all incompatible histories have been eliminated. You are not watching events happen freely and then collide with law. You are watching law quietly decide which sequences are allowed to exist at all. Causality under pressure does not break, it bends, and in bending, it reveals that the universe may not be unfolding step by step, but resolving itself as a whole, enforcing coherence across past, present, and future without ever announcing how it does so. 11. The observer problem. Measurement does not merely reveal reality, it participates in it. Observed systems behave differently than unobserved ones. This is not a philosophical add-on, it is an experimental fact. The universe reacts to being queried, as if outcomes are selected, not sampled. You are accustomed to believing that observation is passive. You look at something, and it remains what it was. A thermometer does not change the temperature it measures in any meaningful way. A camera records an event without altering its course. Observation feels like a window, not an intrusion. At the quantum level, this assumption fails completely. When you observe a quantum system, its behavior changes in ways that cannot be explained as mere disturbance. The act of measurement does not just interfere with the system. It forces the system to take on properties it did not previously possess. Before measurement, certain quantities do not have definite values at all. After measurement, they do. This is not a gap in knowledge. It is a gap in being. You may try to imagine that the system always had definite properties and that measurement simply reveals them. But repeated experiments rule this out. If properties were merely hidden, then statistical correlations would behave differently. They do not. The mathematics insists that outcomes are not pre-written. What exists before observation is not a set of unknown facts. It is a set of unrealized possibilities. This distinction matters because it reshapes the role of the observer. You are not uncovering reality. You are participating in its resolution. The universe does not present a finished picture waiting to be seen. It responds to questions by committing to answers. This response is precise. It is governed by probability distributions. But the selection itself is not random sampling from a pre-existing list. The list is incomplete until the question is asked. The unsettling implication is that reality is not fully defined independent of interaction. You may try to limit this effect to microscopic systems. Surely large objects are immune. Surely the observer problem disappears at scale. Yet every macroscopic system is built from microscopic ones. The transition from undefined to defined does not vanish. It is averaged out. Decoherence explains why quantum effects fade from view, but it does not eliminate the underlying mechanism. The world feels classical because interactions happen constantly, not because measurement stops mattering. The universe is always being observed by itself. This creates a strange feedback loop. Systems interact. Interactions count as measurements. Measurements force outcomes. Outcomes alter future possibilities. The universe is not a static stage. It is a self-interrogating process. This reframes randomness once again. If outcomes are selected rather than sampled, then chance is not the absence of rule. It is the rule governing how selection occurs. The observer does not choose the outcome, but the act of observation constrains which outcomes can exist. You are not free to see anything. You are free to force the universe to decide. This does not mean consciousness causes collapse. The mathematics does not privilege minds. Any interaction capable of recording information counts. A particle colliding with another particle is an observation. A photon scattering is an observation. The universe observes itself relentlessly, and yet the effect remains. Interaction changes reality. This blurs the boundary between subject and object. You are not separate from the system you study. You are embedded within it, subject to the same rules, participating in the same constraints. When you observe the universe observes you back, not intentionally, but inevitably. The discomfort arises from what this says about objectivity. There may be no single, observer-independent account of what exists at all times. There may only be consistent accounts tied to interactions. Reality becomes relational. Events do not happen in isolation. They happen in contexts that include observation itself. Remove the context, and the event loses definition. The observer problem does not suggest that reality is subjective. It suggests that reality is incomplete until engaged. And if that is true, then the universe is not a collection of facts waiting to be discovered. It is a system that resolves itself through interaction, selecting outcomes as it goes, never fully defined until it is forced to be. Randomness does not sit beneath this process. It emerges from it. 12. Information as a physical substance. Information is no longer abstract. It has mass, energy, and consequences. Black holes preserve it. Quantum systems encode it. Physical processes appear driven not just by matter and energy, but by the flow and compression of information itself. You are used to thinking of information as description. Numbers on a page, bits in a computer, patterns that represent something else. In this view, information is secondary. It depends on matter to exist, but it does not shape matter in return. It is passive, weightless. This assumption no longer holds. In modern physics, information behaves like a real quantity. It can be stored, transferred, degraded, and conserved. It obeys limits. It resists destruction. When information is lost, something fundamental has gone wrong. This shift began quietly. Thermodynamics hinted that entropy is not just disorder, but missing information about microscopic states. Later, quantum theory made the connection unavoidable. The state of a system is defined entirely by the information it carries. Change the information, and you change the system. The distinction between what something is and what is known about it begins to collapse. Nowhere is this clearer than in black holes. Once thought to destroy all information that falls into them, black holes forced a crisis in physics. If information truly vanished, the laws of quantum mechanics would break. Probability would fail to add up. Predictability would collapse permanently. This was unacceptable. The resolution was not that information disappears, but that it is preserved in ways that are deeply counterintuitive. Information about everything that falls into a black hole is retained, encoded at its boundary, smeared across its surface, or distributed through subtle correlations. The exact mechanism is still debated, but the conclusion is firm. Information cannot be destroyed. This conservation elevates information to the same status as energy and momentum. It becomes a fundamental bookkeeping requirement of the universe. Processes are no longer judged solely by how matter moves or energy flows, but by how information is transformed. You see this even in ordinary physical systems. Erasing information requires energy. Compressing information generates heat. There are hard limits on how much information can be stored in a given region of space. These are not engineering constraints. They are physical laws. This means that information has consequences, even when no one is reading it. A system evolves not just because forces act on it, but because information flows through it in particular ways. Correlations build, records form, memory accumulates. The arrow of time aligns with the direction in which information spreads and becomes inaccessible. You experience this directly. Memory is information preserved in physical form. Learning changes the structure of your brain. Forgetting corresponds to physical rearrangement. Nothing about thought is free from material constraint. The unsettling implication is that the universe may be fundamentally informational. Matter and energy become carriers. Space and time become frameworks for encoding. What happens is driven not just by dynamics, but by constraints on how information can be arranged and preserved. In this view, randomness takes on a new meaning. Randomness is not the absence of information. It is information you cannot access. A system appears random when its informational structure is too complex, too distributed, or too compressed to decode. Chance is not ignorance of cause. It is ignorance of encoding. This reframes earlier puzzles. The arrow of time aligns with increasing informational entropy. The observer problem becomes a problem of information registration. Measurement creates records. Decoherence spreads information into the environment. Outcomes become definite when information is irreversibly encoded. Reality commits when information is written. Once written, it cannot be erased without cost. This is why events feel final. This is why history accumulates. This is why the universe remembers the past, but not the future. Information gives structure to everything you experience, yet you never perceive it directly. You see matter, you feel energy. But information operates beneath perception, shaping what can occur without announcing itself. If information is physical, then the universe is not just a machine, It is a ledger. Every interaction records something. Every process updates the balance. And nothing that is written can ever be fully removed, only transformed, hidden, or spread so thin that it can no longer be recovered. Randomness does not erase information. It conceals it. And a universe built on concealed information is not indifferent. It is constrained by what must be preserved, no matter how violently events unfold. 13. The universe as a computational process. Some models describe reality as computation. States evolve according to rules, updating from one configuration to the next. In this view, randomness is a tool, not a foundation. It introduces variation, but the computation itself follows strict logic. You are used to thinking of computation as something humans invented. Machines processing symbols, algorithms running on hardware, an artificial activity layered on top of physical reality. But when physicists and mathematicians examine how the universe evolves, the resemblance becomes difficult to ignore. At any moment, the universe occupies a state. That state contains all relevant information about particles, fields, and their relationships. The next moment follows from the previous one according to fixed rules. Inputs are transformed into outputs. Constraints are applied. Possibilities are reduced to a single realized configuration. This is not metaphor. It is how the equations function. In this framework, time is not something that flows. It is an update index, a counter marking successive steps in a transformation process. Each step follows logically from the last, even when the outcome is unpredictable in practice. The unpredictability does not come from lack of rule. It comes from complexity. You already accept this distinction in ordinary computation. A program can be fully deterministic and still impossible to predict without running it. The rules are known. The outcome is not. This gap between determinism and predictability mirrors what you see in nature. The universe may be computing itself. This perspective reframes randomness once again. Randomness becomes a source of input variation, not an absence of structure. It injects noise, seeds diversity, and explores branches of possibility. But it does not override the rules of the computation. It operates within them. A computational system can include randomness without becoming lawless. Random numbers do not free a program from its logic. They only influence which path the logic follows. In this view, the universe does not roll dice blindly. It processes them. You see hints of this in cellular automata, simple computational systems governed by minimal rules. From a handful of instructions, they generate astonishing complexity. Patterns form, structures persist. Order emerges without guidance. The rules do not change. The outcomes vary, but always within the same framework. This resemblance is unsettling because it suggests that complexity does not require intention or chance at the deepest level. It requires rules and iteration. Given enough steps, rich behavior is unavoidable. The universe has had enough steps. If reality is computational, then physical laws are not descriptions of behavior. They are update rules. They specify how one state transforms into the next. Particles, fields, and space-time itself become data structures manipulated by these rules. This does not mean the universe is a simulation. That question is secondary. What matters is that the structure of evolution resembles computation, whether or not there is a computer behind it. The discomfort arises when you realize what this implies about freedom. In a computation, all possible outcomes are implicit in the rules from the beginning. The process unfolds, but it does not invent new rules as it goes. Novelty appears, but only as a rearrangement of what was already allowed. If the universe computes itself, then the space of possible histories was fixed before the first update occurred. Randomness does not expand this space, it only selects paths through it. You might object that quantum randomness introduces genuine novelty, but even quantum randomness follows precise distributions. It does not violate the computational framework. It supplies non-deterministic inputs, but the system's response to those inputs remains rule-bound. This means that unpredictability does not imply openness. A computation can surprise you without being free to do anything at all. The universe may feel alive, creative, and spontaneous, but those qualities may emerge from iteration, not intention. From rule-following processes run at a scale and depth that overwhelms intuition. If this is true, then the unsettling part is not that reality lacks meaning. It is that meaning arises from structure, not chance. The universe does not wander aimlessly and occasionally form order. It executes rules relentlessly, allowing complexity to bloom wherever the computation permits it. Randomness is not the foundation, it is an ingredient. And in a universe that computes itself, even uncertainty plays a prescribed role, advancing the process step by step toward outcomes that were always constrained by logic you never see. 14. Emergence without instruction. Complexity arises from simple rules. Cellular automata demonstrate how intricate patterns evolve from minimal instructions. The universe behaves similarly. Rich structures emerge without guidance, yet always within defined boundaries. The surprise is not emergence itself, but its reliability. You are often led to believe that complexity requires direction, that intricate structures must be assembled deliberately, step by step, by some guiding influence. When you see order, you instinctively look for a planner, a designer, an instruction manual hidden somewhere behind the scenes. But emergence challenges this instinct at its core. In the simplest computational systems ever studied, a handful of rules applied repeatedly generate behavior so complex it becomes unpredictable. No oversight is required. No goals are encoded. The system does not know what it is producing. It simply updates itself according to fixed constraints, and structure appears anyway. This is not a curiosity. It is a warning. The universe behaves in the same way. Elementary interactions repeat endlessly, following unchanging rules. Out of these repetitions arise atoms, chemistry, stars, ecosystems, and minds. None of these outcomes are specified in advance as objectives. They are consequences of iteration under constraint. What unsettles you is not that complexity emerges. It is that it emerges dependably. You can change initial conditions dramatically, and the same classes of structure still appear. Different chemical environments still produce stable molecules. Different planetary systems still form disks, rings, and orbits. Different evolutionary paths still discover similar solutions. The details vary, the forms persist. This reliability suggests that emergence is not accidental. It is enforced. The rules do not instruct the system to build galaxies or brains. They restrict behavior so severely that these outcomes become unavoidable. Complexity is not aimed at. It is what remains after instability is eliminated. This reframes how you understand creation. Nothing is assembled piece by piece. Instead, everything that cannot persist disappears. What survives accumulates. Structure is the residue of constraint. Emergence without instruction feels almost intentional because it produces familiar forms. But there is no foresight involved. The system does not anticipate its outcomes. It simply allows configurations to repeat, amplify, and stabilize when permitted by the rules. You might assume that such emergence would be fragile, that small changes in rules would destroy the effect. Sometimes they do, but often, emergence is robust. Whole families of rules produce similar behavior. Complexity appears not as a fluke, but as a generic feature of rule-based systems. This robustness is disturbing. It suggests that the universe does not need fine-grained direction to produce richness. It needs only constraints and time. Given enough updates, order becomes statistically unavoidable. You see this even in chaotic systems. Despite sensitivity to initial conditions, long-term behavior settles into recognizable patterns. Strange attractors form. Motion explores endlessly, yet never escapes certain shapes. Freedom exists, but only within a cage. The cage is built from rules. This realization undermines a common defense of randomness. You may tell yourself that emergence is just chance amplified, that complexity is the rare outcome of lucky accidents. But emergence does not behave like rarity. It behaves like inevitability once conditions are met. The universe does not try many things and occasionally succeed. It tries very little and succeeds constantly. This has consequences for how you understand novelty. New structures feel creative because they surprise you. But surprise is a limitation of perspective, not of process. The system is not surprised by what it produces. It simply unfolds. If emergence is reliable, then the universe is not experimenting blindly. It is executing constraints that funnel behavior into narrow corridors where structure accumulates naturally. There is no instruction telling matter how to become complex. There is only permission. Permission to persist. Everything you recognize as ordered exists because it was allowed to exist longer than alternatives. Complexity is not built, it is filtered. And a universe that filters relentlessly, producing the same forms again and again without instruction, is not behaving randomly in any meaningful sense. It is behaving lawfully in a way that makes order inevitable, even when no one is trying to create it. 15. Statistical certainty. When systems are large enough, randomness fades, averages dominate, outcomes become predictable. This statistical certainty governs thermodynamics, chemistry, and biology. Chance exists, but it is rapidly overwhelmed by law as scale increases. You encounter randomness most vividly at small scales. A single coin flip feels uncertain. A single particle behaves unpredictably. A single mutation may alter an outcome dramatically. At this level, chance appears powerful, even decisive. It feels as though the universe is improvising. But as systems grow, this impression collapses. Add more coins, and the distribution stabilizes. Add more particles, and temperature becomes well-defined. Add more molecules, and reactions proceed at reliable rates. Variability does not disappear, but it becomes irrelevant. The law of large numbers takes control, forcing behavior into narrow statistical bands. This transition is not gradual, it is overwhelming. Once enough elements are involved, randomness stops being a creative force and becomes background noise. Individual deviations cancel out. Extremes average away. What remains is not freedom, but regularity. This is why thermodynamics works at all. Heat flows predictably because microscopic chaos averages into macroscopic certainty. Pressure exists because countless collisions smooth out irregularities. Entropy increases not as a suggestion, but as a near certainty enforced by scale. You do not need to track every particle to know what will happen. The statistics guarantee it. The same principle governs chemistry. Individual molecular collisions are unpredictable, yet reaction rates are stable. Equilibria form reliably. Complex reaction networks behave consistently across environments. This is not because molecules conspire. It is because large numbers erase randomness. Biology extends this logic even further. Individual organisms vary. Individual mutations are random. But populations evolve predictably under constraint. Traits spread. Structures recur. Entire ecosystems settle into recognizable dynamics. Chance initiates variation. Scale enforces direction. This dominance of statistical certainty undermines the idea that randomness governs reality. Randomness matters locally, temporarily, and weakly. As soon as systems become large enough to matter, law takes over. You may object that rare events still occur. Black swans exist. Unlikely outcomes sometimes dominate history. This is true. But even these extremes are constrained by statistical structure. They occur within distributions that can be modeled, bounded, and anticipated in principle. Unpredictability survives, but it does not rule. The unsettling implication is that freedom shrinks as systems grow. The larger and more interconnected a system becomes, the less room chance has to influence outcomes meaningfully. The universe becomes more predictable as it becomes more complex. This runs counter to intuition. You expect complexity to amplify randomness. Instead, it suppresses it. Large systems behave like machines, not because they are engineered, but because statistics force them to. Behavior becomes locked in. Deviations dampen out. The system forgets its individual components and responds only to aggregate quantities. You see this in your own experience. Your body is made of countless unpredictable processes, yet your temperature stays stable. Your heartbeat follows rhythms. Your metabolism obeys constraints. Local randomness exists, but global order persists. You are not free at the level of molecules. You are constrained at the level that matters. This reveals something deeply uncomfortable. Randomness does not scale well. It thrives only where impact is minimal. As soon as consequences accumulate, it is drowned out by averages. The universe seems structured to ensure this outcome. Laws do not loosen with scale. They tighten. Constraints become more effective. Predictability increases, not decreases. Statistical certainty does not eliminate uncertainty. It renders it harmless. And this suggests that randomness may never have been intended as a foundation. It may be a byproduct of smallness, a feature that vanishes when reality becomes large enough to sustain structure, memory, and history. The universe tolerates chance briefly. Then it overwhelms it. And in doing so, it reveals that unpredictability is not the driving force of existence. It is something reality allows only until numbers, connections, and constraints quietly take control, forcing outcomes to settle into paths that were always statistically inevitable. 16. Selection without choice. In evolution, mutations are random, but selection is not. Environments filter outcomes relentlessly. Over time, order increases locally, not by intention, but by constraint. This same logic may operate at cosmic scales, selecting stable universes over unstable ones. You are taught that evolution is driven by chance. Mutations occur without foresight. Variations arise blindly. This framing is correct, but it is incomplete. Chance introduces differences, but it does not decide which differences persist. That decision is made by the environment, and the environment does not negotiate. Selection is absolute. Every organism exists within constraints it did not choose: temperature, chemistry, competition, available energy. These conditions eliminate most variations immediately. Only a narrow subset can survive long enough to matter. Over time, this filtering produces the appearance of direction, even though no direction was intended. Order increases not because something wants it to, but because instability is removed. This distinction is subtle, but essential. Evolution does not climb toward complexity because complexity is favored. It accumulates structure because simple, unstable arrangements fail to persist. What remains grows layered and intricate because it has already passed countless filters. Selection without choice produces results that feel purposeful. The same logic applies far beyond biology. In chemistry, unstable molecules decay. In physics, unstable particles vanish. In astrophysics, unstable orbits collapse. At every scale, configurations that cannot maintain themselves are erased quickly. Stability is not selected consciously. It is selected by survival time. Persistence becomes the metric of success. When you look at the universe this way, randomness appears less powerful. It generates options, but almost all options die immediately. The environment, defined by physical law, enforces ruthless elimination. What survives appears special only because everything else disappears too fast to observe. This raises a disturbing possibility. What if the universe itself is subject to a form of selection? You may assume that the laws of physics are fixed, that there is only one universe, one rule set. But some theoretical models suggest otherwise. They allow for multiple possible universes, each with different constants, structures, or dimensions. Most of these universes would be unstable. They would collapse instantly, expand too rapidly, or fail to support any coherent structure. Only a few would persist. If such a landscape exists, then what you observe is not a random universe. It is a surviving universe, not because it was chosen, but because it did not eliminate itself. Selection without choice scales up. This idea does not require intention. It does not require design. It requires only that unstable configurations disappear faster than stable ones. Over enough trials, the survivors dominate observation. You never see the failures. This logic is unsettling because it reframes fine-tuning, order, and structure as consequences of filtering rather than accident. The universe may appear balanced, not because balance was aimed at, but because imbalance is fleeting. The same mechanism that produces complex life from random mutation could produce a structured cosmos from random initial conditions. Chance proposes. Constraint disposes. The universe you inhabit may not be typical. It may be exceptional precisely because typical configurations do not last. This undermines the comforting narrative of neutrality. A neutral process would treat all outcomes equally. Selection does not. It enforces asymmetry relentlessly. Survivors accumulate structure simply because they are allowed to continue. You are not the product of random mutation alone. You are the product of everything that failed before you. Extend this logic outward, and the implication becomes heavier. The laws you observe may not be fundamental truths. They may be the residue left behind after countless alternatives erased themselves. The universe may not be optimized. It may be filtered. Selection without choice produces order without purpose, direction without intent, and structure without guidance. It feels almost deliberate because it is so effective. But effectiveness does not require planning. It requires only time and constraint. And if this logic governs reality at every scale, then randomness has never been in charge. It has only been tolerated long enough for stability to emerge. 17. The multiverse escape. Some propose infinite universes to preserve randomness. If everything exists somewhere, then order here is unsurprising. But this does not remove structure. It relocates it. The multiverse itself must obey rules that allow such variation. When confronted with fine-tuning, order, and improbability, the multiverse appears as a release valve. If there are infinitely many universes, each with different laws and constants, then it is no mystery that one of them looks like this. You find yourself in a universe compatible with your existence simply because incompatible universes cannot host observers. At first, this reasoning feels decisive. It dissolves unease by inflating possibility. But when you examine it carefully, the relief fades. The multiverse does not eliminate structure. It multiplies it. It replaces one highly constrained universe with a highly constrained generator of universes. The burden of explanation is not removed. It is displaced. For a multiverse to exist at all, there must be a mechanism that produces universes. That mechanism must follow rules. It must permit variation without collapsing into incoherence. It must define which constants can change, how they change, and within what limits. Infinite outcomes do not arise from infinite freedom. They arise from structured processes capable of variation. Randomness alone cannot generate a multiverse any more than it can generate a stable universe. Even if universes vary, the space of variation is not arbitrary. Certain parameters must remain fixed for any universe to exist long enough to count. Others may fluctuate, but only within ranges that preserve consistency. A truly unconstrained multiverse would not produce universes. It would produce nothing that persists. The multiverse, if real, would be filtered just like everything else. This reveals the core problem. Appealing to infinity feels like an escape because it dilutes improbability. But dilution is not explanation. Saying that every outcome exists somewhere does not explain why outcomes exist at all, nor why they obey mathematical structure rather than dissolving into noise. Infinity does not replace law, it requires it. You may argue that the multiverse restores randomness at the deepest level, that while individual universes are ordered, the ensemble is chaotic. But chaos at one level does not negate constraint at another. The distribution of universes would still follow rules. Some types would dominate. Others would be rare or non-existent. Selection reappears. Only universes that persist can be counted. Only universes that support structure can be observed. Only universes that obey coherence can even be defined. The multiverse does not avoid these filters. It amplifies them. This creates a subtle trap. By expanding the scope of explanation, you risk obscuring the very thing you are trying to explain. The question is not why this universe exists among many. The question is why the process that generates universes is so tightly constrained that stable, law-abiding realities emerge at all. The multiverse may be vast, but it is not free. If you trace the logic far enough back, you arrive at the same discomfort. Whether there is one universe or many, the underlying framework must enforce consistency, stability, and rule-following behavior. Randomness alone cannot do this. It must be shaped. The multiverse does not restore indifference. It relocates necessity to a deeper layer, one you cannot observe directly. The rules are still there. They are simply hidden behind scale. This is why the multiverse feels both explanatory and evasive. It answers how improbability can occur without answering why constraint exists at all. It explains selection without explaining the origin of what is being selected. You are left with the same conclusion, only farther away. Reality is not random at its foundation. Even infinity must obey structure. And a universe born from a multiverse is still born from rules that refuse to let everything happen. 18. Mathematical reality. Mathematics predicts phenomena before they are observed. Equations describe particles that later appear. This effectiveness is not guaranteed by randomness. It suggests a deep alignment between abstract structure and physical existence. You are taught that mathematics is a tool. a language invented to describe patterns you already see. Numbers summarize, equations compress, symbols organize experience after the fact. In this view, mathematics follows reality. It reacts to what exists. But again and again, reality reverses this order. Long before experiments confirm them, mathematical structures point to entities that have never been observed. Particles appear on paper before they appear in detectors. Forces are inferred from symmetry long before they are measured. Entire frameworks predict behavior that seems impossible until reality complies. This is not coincidence. If mathematics were merely descriptive, its success would be limited. It would approximate. It would fail often. Instead, it succeeds with an accuracy that borders on the unsettling. Equations written decades earlier continue to predict outcomes to extraordinary precision. Randomness does not explain this. There is no reason to expect abstract symbols, developed in isolation, to map so precisely onto the behavior of the physical world. You could imagine a universe where mathematics works only locally, or loosely, or not at all. A universe where patterns exist but cannot be captured by formal structure. You do not live in that universe. Instead, you inhabit one where mathematical consistency seems to precede observation, where logical necessity constrains physical possibility, where entire classes of phenomena are ruled out not by experiment, but by proof. This alignment raises an uncomfortable question. Why should reality obey mathematics at all? One answer is that mathematics is discovered, not invented. That abstract structures exist independently, and the universe instantiates a subset of them. In this view, reality is mathematical at its core. Physical existence becomes a particular solution to a deeper logical system. Another answer is more conservative. Mathematics works because it encodes symmetry, constraint, and consistency, which any stable universe must obey. But even this explanation concedes the point. Stability itself requires alignment with abstract structure. Either way, mathematics is not optional. You see this when equations fail. When mathematical inconsistency appears, theories collapse. Predictions become meaningless. Entire models are discarded not because they conflict with data, but because they violate internal coherence. Reality does not tolerate contradiction. This intolerance suggests that mathematics is not just a mirror, it is a filter. Only mathematically consistent realities are allowed to exist. This reframes randomness again. Random outcomes still occur, but only within spaces defined by mathematical structure. The dice can roll, but only on surfaces shaped by logic. Outcomes are free to vary, but not free to contradict. You may find comfort in thinking that mathematics simply happens to match reality because we refined it to do so. But this explanation breaks down when mathematics predicts phenomena no one was looking for. When equations lead and observation follows, the direction of explanation reverses. The universe behaves as if it is reading the same rules. This does not mean the universe is conscious or intentional. It means that physical existence may be constrained by abstract necessity, that what can happen is limited not just by energy and matter, but by what is logically self-consistent. In such a universe, randomness cannot be foundational. Foundational randomness would produce contradiction. It would generate outcomes that violate structure. That does not happen. What happens instead is selection at the level of possibility. Only mathematically coherent patterns survive long enough to be called real. This is why mathematics feels uncannily effective. It is not describing reality from the outside. It is carving out the space in which reality is allowed to appear. The unsettling implication is that the deepest layer of existence may not be physical at all. It may be abstract, logical. independent of time, space, or matter. You do not live in a universe that merely happens to obey mathematics. You live in a universe that could not exist if it did not. And once you accept that, randomness retreats further from the foundation. It becomes something that operates inside a framework that was never negotiable. Reality does not invent its structure as it goes. It instantiates what mathematics already permits. 19. Compression over chaos. Physical laws often reduce complexity. Diverse systems collapse into simple descriptions. This compression implies efficiency. Random processes generate information. Laws remove it. The universe appears biased toward simplification. You tend to associate complexity with richness, more detail, more variation, more freedom. In that framing, compression feels like loss, like something being flattened or erased. But in physics, compression is not a failure of description. It is the signal that something fundamental has been understood. When a single equation replaces thousands of observations, nothing essential has been lost. The equation has captured what matters and discarded what does not. This is not coincidence. It is how physical law operates. Across domains, wildly different systems reduce to the same simple principles. Gases with countless molecular configurations obey a small set of thermodynamic variables. Planetary motions collapse into a few conserved quantities. Electrical phenomena reduced to compact field equations. Complexity recedes as scale increases. This is not how randomness behaves. Randomness generates detail. It produces variation without preference. Given enough time, it fills space with noise. Compression does the opposite. It strips away difference, leaving only what persists across change. It identifies invariance. The universe seems to favor this process. When systems evolve, they often shed information. Fine-grained details disappear into heat. Microscopic distinctions blur. Macroscopic behavior becomes simpler, not more complex. Many degrees of freedom collapse into a few collective variables that dominate behavior. This is not accidental. It is enforced. The laws of physics actively remove information from your access. Entropy increases because information about exact states spreads into correlations you cannot track. What remains is a compressed description that governs everything you can measure. You never see the full complexity. You see its shadow. This bias toward compression is unsettling because it suggests that the universe does not value detail. It values stability. Laws do not preserve every distinction. They preserve only those that survive aggregation, averaging, and interaction. Randomness may generate information locally, but law erases it globally. This is why prediction improves with scale. The more components involved, the fewer variables you need to describe the outcome. The universe becomes easier to summarize as it becomes larger. Chaos is domesticated by numbers. You might expect the opposite, that more components would require more explanation. But reality inverts this intuition. Large systems forget their parts. They remember only totals, averages, symmetries. This forgetting is not a limitation of measurement. It is a feature of dynamics. Once information disperses beyond recovery, it no longer influences future behavior. It has been compressed out of relevance. The universe does not keep redundant records. It moves on. This reveals a deep asymmetry. Randomness can create information, but it struggles to preserve it. Laws, by contrast, excel at erasing distinctions. They funnel behavior into narrow channels where only a few variables matter. This is why physical theories trend toward unification. Separate phenomena turn out to be manifestations of the same underlying structure. Complexity collapses into simplicity, not because reality is simple, but because it refuses to maintain unnecessary detail. The universe is economical. This economy undermines the idea that reality is exploring possibilities freely. Exploration produces variety. Compression eliminates it. The fact that the universe repeatedly compresses suggests that exploration is secondary. What matters is convergence. Even when complexity emerges temporarily, it does so within bounds. Structures form, interact, and dissolve, but the laws that govern them remain compact. The same equations apply regardless of scale, context, or history. This persistence implies bias, not toward chaos, but away from it. The universe tolerates complexity only as long as it does not obstruct compression. Once detail ceases to influence large-scale behavior, it is discarded. Laws do not care about stories. They care about invariance. You experience this personally. Your memories fade, details blur. What remains are summaries, patterns, meanings. Compression shapes not just physics, but cognition. What you remember is what mattered statistically. This parallel is not accidental. A universe that compresses relentlessly is not neutral toward information. It actively reduces it to what must be preserved. Randomness may scatter, but law gathers. Randomness may explore, but law decides what survives compression. The unsettling conclusion is not that the universe is simple. It is that it is biased toward making itself simple enough to persist. Chaos is tolerated briefly. Compression is permanent. And in a reality that constantly compresses, randomness can never be the final authority. It is something the universe allows only until law removes it from relevance, leaving behind structures so stable they appear inevitable. 20. Constraints that feel like preference. When certain outcomes dominate again and again, it begins to resemble choice. Not conscious choice, but directional behavior. The universe favors paths of least resistance, maximum symmetry, and stable configurations. You hesitate to use the language of preference. It sounds anthropomorphic, dangerous, as if you are smuggling intention into equations. So you replace it with safer words: constraint, optimization, minimization. But the behavior remains the same. Certain paths are taken repeatedly. Others are avoided so reliably they might as well not exist. The universe does not wander evenly through possibility space. It funnels. Energy flows toward lower states. Systems relax into equilibrium. Structures settle into configurations that distribute stress evenly and conserve invariance. These outcomes are not forced one by one. They are favored globally. Given enough time, almost every process ends the same way. This looks less like neutrality and more like direction. You may insist that this direction is illusory, that it arises purely from mathematics, that no outcome is wanted. But even mathematics encodes bias. Equations are not symmetric with respect to all possibilities. They privilege solutions that minimize action, reduce gradients, or preserve symmetry. The universe follows these solutions not because it must, but because alternatives collapse. This is the unsettling part. If constraints eliminate most options before they can manifest, then what remains begins to look intentional simply because it is consistent. The universe does not try many things and occasionally succeed. It tries very few things and succeeds almost every time. Paths of least resistance dominate not because they are chosen, but because resistance destroys alternatives. Maximum symmetry appears not because symmetry is valued, but because asymmetry is unstable. Stable configurations recur because instability cannot survive. This creates a one-way pressure in possibility space. You see this pressure everywhere. Rivers carve predictable paths. Cracks propagate along stress lines. Crystals grow into regular shapes. Orbits settle into planes. Even abstract systems behave this way. Algorithms converge. Learning stabilizes. Markets drift toward equilibria. Different domains, same direction. At some point, the language of preference stops feeling metaphorical. When behavior is so consistent across scale, explanation shifts. You stop asking why outcomes repeat and start asking why anything else ever happens at all. Randomness still exists, but it feels subordinate. It introduces variation, but variation is quickly sorted. Deviations are corrected. Extremes dampen out. The universe behaves like a system with a built-in sense of where it is allowed to go, not where it wants to go, where it can survive going. This distinction matters. Preference implies desire, constraint implies necessity. But from the inside, the difference blurs. If only certain paths ever persist, then behavior acquires direction whether or not intention exists. You cannot meaningfully distinguish between a system that prefers stability and one that eliminates instability. The outcome is the same. The discomfort comes from realizing that indifference would look different. A truly indifferent universe would explore evenly. It would tolerate chaos. It would not repeatedly settle into the same shapes, the same distributions, the same balances. But this universe does. Again and again, it chooses the same endings. You may try to explain this away by invoking probability. High probability outcomes occur more often. Low probability ones do not. But probability itself is a measure of preference encoded mathematically. It tells you which outcomes dominate. It does not explain why dominance exists. Constraints are not passive. They actively sculpt behavior. When action is minimized, when symmetry is restored, when energy gradients flatten, the universe is not merely obeying equations. It is exhausting alternatives. It is collapsing freedom into inevitability. This is why the language of preference keeps returning, not because the universe chooses, but because its constraints behave as if they do. They push reality toward the same resting places regardless of starting point. The universe feels directional because it is, not toward a goal, toward survival. And once you see that, randomness stops feeling like the guiding principle. It becomes a disturbance that is tolerated briefly, then erased, as the universe settles back into the few configurations it always seems to favor. Constraint does not think, but it decides. And in a universe governed by such decisions, indifference is an illusion that does not survive repeated outcomes. 21. Noise as a secondary feature. Randomness may not be primary. It may arise from incomplete access to underlying structure. What looks like noise could be the surface of deeper order, too fine-grained to resolve directly. You instinctively treat noise as fundamental. When a signal becomes erratic, when outcomes scatter unpredictably, you assume the process itself has lost structure. Disorder feels like the default explanation when patterns disappear from view. Randomness becomes the final layer beneath which nothing meaningful remains. But this assumption quietly reverses how science has progressed. Again and again, what once appeared as irreducible noise has been revealed as structure operating beyond resolution. Thermal motion was once chaos until molecular theory exposed orderly collisions. Brownian motion looked random until atomic reality was uncovered beneath it. Static on a screen masked signals too compressed to decode. Noise was never the foundation. It was a limit. This pattern repeats at every scale. When you cannot track all variables, behavior becomes unpredictable. When interactions multiply beyond accounting, outcomes blur. Randomness appears not because rules vanish, but because they exceed your capacity to follow them. Noise is what structure looks like when it outruns observation. This distinction matters because it reframes uncertainty. If randomness is fundamental, then unpredictability reflects freedom at the core of reality. But if randomness is secondary, then unpredictability reflects ignorance, not indeterminacy. What you call chance is the shadow cast by complexity. Even quantum randomness may fit this pattern. Outcomes appear probabilistic, but probabilities themselves are rigidly defined. Distributions remain stable. Forbidden results never occur. This suggests that randomness is constrained by rules too deep to access directly. You do not see chaos. You see unresolved order. This becomes clearer when you examine systems with hidden correlations. What looks like independent noise often turns out to be structured once additional dimensions are considered. Variables that seem unrelated become tightly linked when viewed from a higher perspective. The universe may operate the same way. Reality could be deeply ordered at a level you cannot probe, with randomness emerging only because that order is compressed, distributed, or encoded in forms inaccessible to direct measurement. Noise becomes a byproduct of scale separation. You experience this personally. Your thoughts feel spontaneous. Your decisions feel free. Yet neuroscience reveals layers of structure beneath awareness. Signals propagate, thresholds trigger, patterns repeat. What feels random from the inside reveals order when examined from the outside. Subjective noise hides objective structure. The same may be true cosmically. The universe you observe may be a coarse-grained projection of a far more detailed process. Laws describe averages. Probabilities summarize ignorance. Randomness fills the gaps where resolution fails. This does not trivialize uncertainty. It deepens it. Because if noise is secondary, then every apparent accident carries hidden necessity. Every random fluctuation sits atop constraints you cannot see. Events are not free. They are opaque. This is more unsettling than true randomness. True randomness would mean the universe sometimes genuinely does not know what it will do. Secondary noise means the universe knows exactly what it is doing, but you do not. In this view, randomness is not a feature the universe relies on. It is a concession it makes to observers with limited access. It is what you experience when the system is too large, too fast, or too interconnected to follow in detail. Noise protects structure by concealing it. You may resist this idea because it removes a comforting boundary. If randomness is not fundamental, then there is no final refuge where explanation stops. There is always another layer beneath, even if it is unreachable in practice. Uncertainty becomes epistemic, not ontological. This does not imply determinism in the classical sense. Complex systems can be rule-bound and still unpredictable. But unpredictability no longer signals absence of order. It signals excess of it. The universe may not be random because it lacks rules. It may appear random because it has too many. And if that is the case, then the surface chaos you observe is not evidence of freedom at the foundation of reality. It is evidence of compression, projection, and loss of access. Noise is not what remains when order disappears. Noise is what order becomes when you cannot see it clearly enough to recognize it. And in a universe where noise is secondary, randomness retreats once more from the foundation, leaving behind the uncomfortable possibility that beneath every accident lies a structure you are never allowed to fully observe. 22. The limits of prediction. Even with perfect laws, some outcomes remain unpredictable. This does not, imply freedom. It implies sensitivity. Small differences amplify. Chaos theory shows how deterministic systems can mimic randomness without being random at all. You often equate unpredictability with openness. If an outcome cannot be predicted, you assume it was not determined. This intuition feels natural. Prediction seems tied to control, and control feels tied to law. Where prediction fails, freedom appears to enter. But this connection is misleading. There are systems whose rules are known perfectly, yet whose future behavior cannot be forecast beyond short horizons. Not because the rules are incomplete, but because the systems are exquisitely sensitive. Infinitesimal differences in initial conditions grow exponentially, quickly overwhelming any measurement precision. This is chaos. In a chaotic system, the future is fixed in principle but unknowable in practice. The equations determine everything. Nothing is left to chance. And yet, prediction collapses almost immediately. Two nearly identical starting points diverge so rapidly that long-term forecasts become meaningless. This behavior feels random. It produces irregularity, surprise, and apparent noise, but it is not randomness. It is law operating under sensitivity. You encounter this every day. Weather systems follow deterministic equations, yet long-term forecasts fail. Fluid turbulence obeys precise laws, yet its motion appears erratic. Planetary systems can become chaotic over long timescales, even though gravity is fully understood. The failure is not in the rules. It is in your ability to track them. This distinction matters because it dismantles a common refuge for randomness. When prediction fails, it is tempting to conclude that outcomes are not determined. But chaos shows that unpredictability can arise even when every step is rule-bound. Freedom does not follow from surprise. The universe does not need randomness to generate unpredictability. It only needs sensitivity. This sensitivity has a profound consequence. It means that knowledge has limits that cannot be overcome by better instruments alone. No matter how precisely you measure, there will always be a horizon beyond which prediction dissolves, not because reality is undecided, but because differences too small to detect have already sealed the outcome. From your perspective, the future looks open. From the system's perspective, it is already constrained. This creates a subtle illusion. You experience uncertainty and interpret it as indeterminacy. But uncertainty is about access, not about structure. It describes what you can know, not what exists. Chaos exposes this gap brutally. Even if the universe were entirely deterministic, it would still appear random in many contexts. Not because laws are absent, but because their consequences outrun comprehension. This undermines the idea that randomness is necessary to explain unpredictability. Apparent chance can emerge from law just as readily as order can. The boundary between the two is not sharp. It depends on scale, precision, and sensitivity. You may object that quantum uncertainty is different, that it introduces genuine indeterminacy. But even here, the outcomes are bounded, distributed, and constrained. Quantum randomness does not grant unlimited freedom. It operates within strict frameworks that resemble chaotic amplification more than creative choice. The limits of prediction do not rescue randomness as a foundation. They expose its weakness. Unpredictability is not evidence that the universe is undecided. It is evidence that complexity hides decisions from you. This realization is unsettling because it removes another comforting boundary. There is no clean line where law stops and chance begins. There is only a continuum where law becomes too sensitive to follow. The universe may be fully constrained and still feel open, fully rule-bound and still surprise you endlessly. Your inability to predict does not grant freedom to reality. It reveals your distance from its workings, and in that distance, randomness appears not as a fundamental feature of existence, but as a name you give to the region where law continues operating long after your understanding has failed to keep up. 23. Meaning without intention. Order does not require purpose, but it does undermine indifference. A universe that consistently produces structure is not neutral. It has direction, even if that direction is impersonal. You are quick to separate meaning from mechanism. Meaning, you are told, belongs to minds. Mechanism belongs to matter. If the universe lacks intention, then it must also lack meaning. Whatever structure appears is incidental, a side effect of blind processes that do not care what they produce. This conclusion feels safe because it draws a clean boundary. No intention means no direction. No direction means no implication. The universe happens, and you interpret. But this boundary begins to blur when structure appears reliably. A universe that produces order once could be dismissed as lucky. A universe that produces order everywhere, across scales and conditions, cannot be dismissed so easily. Repetition transforms coincidence into character. Consistency transforms accident into behavior. The universe does not merely allow structure. It generates it relentlessly. This does not imply purpose. No goal is required. No plan is executed. But indifference begins to look implausible when outcomes align again and again, when laws funnel matter into stable forms, when complexity accumulates instead of dissolving, when patterns recur regardless of where or when you look. Indifference would look different. An indifferent universe would explore without bias. It would tolerate incoherence. It would not repeatedly converge on the same solutions. It would not favor stability, symmetry, or persistence. Yet this universe does all of these things, relentlessly and without exception. Direction emerges without intention. This distinction matters because it reframes meaning. Meaning does not have to be imposed from outside. It can arise from constraint. When behavior is shaped consistently, it acquires significance, whether or not anyone intended it. Consider a river. It does not intend to reach the sea. It does not plan its course, yet it flows in one direction, carving landscapes, shaping ecosystems, creating boundaries and paths that persist for millennia. Its direction is not chosen, but it is real. The universe behaves similarly. It flows toward equilibrium. It concentrates matter under gravity. It amplifies stability and erases instability. These tendencies do not express desire, but they do express orientation. Reality leans. You may resist calling this meaning because it lacks consciousness, but meaning does not require awareness. It requires structure that persists and constrains what follows. A stop sign has meaning because it shapes behavior, not because it knows what it does. The laws of physics shape everything that happens next. This shaping undermines the idea that the universe is neutral. Neutrality would imply no favored paths, no recurring outcomes, no stable forms. Yet neutrality is absent at every level you examine. From particles to galaxies, from chemistry to life, structure accumulates and endures. Meaning emerges not from intention, but from inevitability. This realization is unsettling because it removes a familiar refuge. You cannot dismiss the universe as a meaningless backdrop simply because it lacks a mind. Its behavior still carries implication. It still constrains. It still directs. You are embedded in this directionality. Your body, your thoughts, your memories are products of the same processes that favor order over chaos. You exist because instability was filtered out long before you appeared. This does not grant cosmic purpose. It grants context. A universe that consistently produces structure is a universe in which events are not interchangeable. Some outcomes matter more because they persist. Some paths dominate because others disappear. This hierarchy exists whether or not it was designed. Meaning, in this sense, is not something added to reality. It is something revealed by how reality behaves. You are not projecting significance onto a blank slate. You are recognizing direction in a system that cannot avoid producing it. The universe does not tell a story on purpose, but it does not remain silent either. It speaks through repetition, through constraint, through the elimination of alternatives. Meaning, without intention, is quieter than purpose, but it is harder to deny. And once you recognize it, the idea of a universe that is truly indifferent begins to feel less like a conclusion and more like a comforting assumption you were never required to make. 24. You as a product of constraint. Your thoughts, memories, and choices arise from physical processes shaped by these same laws. If the universe is not random, then neither are you in the way, you assume. Your existence follows from necessity layered upon chance. You are used to locating freedom inside yourself. Your decisions feel spontaneous. Your thoughts feel uncaused. When you act, it feels as though alternatives were genuinely open until the moment you chose. This sense of authorship is intimate and convincing. It feels like the final refuge from an ordered universe. But when you trace your experience downward, that refuge begins to narrow. Your brain is a physical system. It obeys the same principles that govern everything else. Electrical signals propagate along neurons. Chemical gradients trigger thresholds. Networks reinforce certain pathways and weaken others. Memory is not an abstract archive. It is a pattern etched into matter. Nothing about this process is exempt from constraint. This does not mean your thoughts are simple or predictable. Complexity thrives here. Sensitivity amplifies. Feedback loops create novelty. But novelty does not imply independence. It implies layered structure operating at scales too deep to introspect. What you experience as a choice is the resolution of competing processes shaped long before awareness enters the picture. This realization is uncomfortable because it threatens a cherished boundary. If you are a product of constraint, then freedom must be redefined. It cannot mean exemption from law. It cannot mean randomness either. Randomness would not give you agency. It would remove coherence. Your actions are neither fully free nor fully random. They are conditioned. You inherit constraints from biology, from chemistry, from physics. Your nervous system did not choose its architecture. Your cognitive biases were not selected deliberately. Your emotional responses reflect ancient survival pressures encoded long before you existed. Chance plays a role. Random mutations, unpredictable environments, contingent experiences. But chance operates inside a framework it did not design. It introduces variation. Constraint determines what persists. Your identity emerges from this interaction. You are not written by fate, but you are not written on a blank page either. The space of who you can become is bounded by laws you never see and cannot violate. Some thoughts feel natural, others feel impossible. Some choices feel available, others never even present themselves as options. Constraint shapes possibility before choice occurs. This does not make you irrelevant. It makes you situated. Your decisions matter precisely because they occur within limits. A move in chess matters because rules restrict movement. Without constraint, no action would carry weight. Freedom without boundaries, dissolves into noise. The unsettling part is not that you are constrained. It is that the constraints are doing most of the work. You feel like an exception because you experience deliberation. But deliberation itself is a process governed by thresholds, timing, and reinforcement. The sense of deciding arrives after conditions align. Awareness witnesses commitment more than it initiates it. This does not make you a machine in the trivial sense. Machines are simple. You are layered, recursive, sensitive to context. But every layer rests on another that obeys law without negotiation. You are a product of necessity layered upon chance. Chance shaped variation. Necessity filtered it. What survived became you. This reframes responsibility, identity, and meaning in uncomfortable ways. You cannot retreat into randomness to claim freedom, nor into determinism to deny relevance. You exist in a narrower space where structure produces experience without consulting intention. The universe does not single you out. It produces you the way it produces everything else, through constraint. Your thoughts are not exempt from physics. Your memories are not exempt from entropy. Your choices are not exempt from causation. They are expressions of it, arriving at scales where complexity feels like authorship. You are not less real because you are constrained. You are real because you are constrained enough to persist. And if the universe is not random at its foundation, then neither are you in the way you were taught to believe. You are not an accident floating in chaos. You are a configuration that was allowed to exist, briefly, precisely, and only within the narrow corridor that reality has always permitted. 25. The question that remains. If randomness is not fundamental, then unpredictability is not the same as freedom. And if outcomes are constrained from the start, then reality may be less open than it appears. The universe may not be rolling dice. It may be following a path you are only beginning to see. You reach this point expecting resolution, a final answer that restores balance. Either randomness reigns or structure does. Either the universe is free or it is fixed. But the deeper you descend, the less these oppositions hold. What you are left with is a question that refuses to settle. If unpredictability can arise from law, if chance can be a surface effect of constraint, then uncertainty loses its role as evidence of openness. The future may feel undecided not because it is free, but because the mechanisms shaping it are too deep, too distributed, or too compressed to track. This realization quietly alters everything. You can no longer rely on randomness as a guarantee of neutrality. You can no longer point to surprise as proof that nothing is guiding outcomes. Surprise may only signal that the guidance is hidden. At the same time, you cannot replace randomness with intention. Nothing you have seen requires purpose, desire, or planning. The universe does not aim. It does not care. It does not watch. And yet, it behaves consistently. It filters relentlessly. It favors stability. It enforces coherence. This combination is what unsettles you. A universe with intention would be easier to confront. A universe of pure chaos would be easier to dismiss. But a universe governed by impersonal constraint, producing order without awareness, offers no comfort. It does not promise meaning. It does not guarantee freedom. It simply insists. If outcomes are constrained from the start, then the openness you experience is partial. You move within a space that feels vast but is already shaped. Possibilities branch, but only along channels that were carved before you arrived. The future unfolds, but not arbitrarily. You are not watching dice roll. You are watching a system resolve itself. This does not mean everything is predetermined in a simple sense. Sensitivity, complexity, and scale ensure that prediction remains limited. Novelty still appears. History still surprises. But surprise is no longer evidence that anything could have happened. It is evidence that you could not see what was allowed to happen. This reframes freedom in a way that is deeply uncomfortable. Freedom becomes local, not absolute. It exists within constraint, not beyond it. You act, choose, and decide, but always inside boundaries you did not set and cannot escape. The universe does not ask what you want. It asks what is permitted, and it has been asking that question since the beginning. What remains unresolved is not a scientific detail, but a philosophical wound. If reality is less open than it appears, then the stories you tell yourself about chance, agency, and possibility require revision. You are not drifting through an indifferent void. You are moving through a structure that existed before you and will continue after you. This structure does not explain itself. It does not announce its origin. It simply operates. The question that remains is not whether the universe is random or determined. It is whether openness itself is something you inferred because you needed it to be true. Whether freedom felt necessary because the alternative felt unbearable. If randomness is not fundamental, then uncertainty is not liberation. It is obscurity. And if the universe is following a path, then you are not outside that path observing it. You are part of it. The unsettling possibility is that reality is not becoming something new. It is revealing something old, and the more closely you look, the more it feels as though the dice were never rolling at all.